We were discussing about LNS, and the first prototype which seemed to work, which is having not an explicit input resistance, is this one. If we are interested in only the short circuit current, so we were trying to see how can we manufacture a Z-in. How can we manufacture a Z-in which had a real component without using an explicit resistance, right? If you just put an explicit 50 ohm resistance, it is going to have a real component, but that gives you additional noise, right? Additional power, moment you have a lossy element, it is going to consume power and it is going to give you some noise. So, so if you have an explicit resistor or a resistor mimicking device, then you cannot really do much better than 3 dB noise figure. So then the quest was, can we think of something which gives you an equivalent real impedance without using an explicit resistor? Then we saw that if you have negative feedback or any sort of feedback or any sort of phase lag between two nodes, and you put a capacitor or for that matter even an inductor, then depending upon the type of phase lag, it is possible to get a real positive impedance looking into any node, and it need not necessarily be for this particular architecture. It can be for any other architecture. But the key thing is to note that whenever you put a capacitor or an inductor, you have to ensure that the phase lag still exists, right? So otherwise, you are not going to get any difference. Okay, fine. So if that is the case, then we saw that this Z-in. So this was CGS. LS. Then we saw that Z-in was equal to, obviously, the summation of the impedance provided by CGS and LS, that should be there. So J omega LS plus 1 by J omega CGS, plus we had a real term, which was omega t times LS, where omega t is GM by CGS. So this is the GM, right? The transconductance of the transistor is the GM. So then we said that, okay, so it looks like we have a real term, but we also have these imaginary terms. But if we can resonate out the inductor and the capacitor at certain frequency, then we are good, right? So then if this is equal to this, so this is the condition for resonance, then your Z-in exactly equal to omega TLS, which you manufacture, which you design for a 50 ohm load, assuming RS is 50 ohm, and then you essentially get the perfect impedance match looking at the input. And note that it does not use any explicit 50 ohm resistor or explicit RS, right? It is getting manufactured by this current control, the voltage control current source and some feedback around it. Okay, fine. So this is where we ended. So now today we are going to look at this in a bit more detail and see whether there are some nuances to it, or we can simply say that, okay, this is it, right? So when you are designing, you'll have to then ask the questions that how do I, okay, this architecture probably seems to work, but how do I size the transistor, right? How do I size CGS? How do I size LS? So before doing that sizing business, let's look at the fundamental thing that an amplifier is supposed to do is, can it give us gain, right? So, and if it gives us gain, what is the gain that we are going to get? And if we want to maximize gain, what are the handles that we have? So This is what we have at the moment. And I'm interested in the short circuit current because ultimately if I have a resistor, current is going to add up. I mean, get multiplied with the value of the resistance. So that doesn't really matter at this moment. So we will assume that it has been matched, right? Assuming omega T Ls is equal to Rs, that is, it has been matched. Then what is the impedance looking here? Rs, right? The impedance looking here is Rs. So what will be the current to the source? Pardon? V in over 2Rs, right? Rs given by the matching network and Rs it has already, V in by 2Rs. So this current is essentially flowing through the CGS because the capacitor of the capacitance associated with the MOSFET has been lumped into CGS. So MOSFET is, in this configuration, the MOSFET input impedance is infinite. So this entire current flows into CGS. So the VGS that it develops is essentially this current times the impedance provided by the capacitor. So essentially V in by 2Rs times 1 by J omega CGS, right? Okay. So your I out then is essentially GM times VGS, which is V in by 2Rs times GM by J omega CGS, right? So which essentially means that the effective transconductance, right? So this effective transconductance of this LNA, right from V in to output, is essentially GM by CGS is omega T. So this is 1 by 2Rs. If I just say mod, then 1 by 2Rs, omega T, omega by omega, sorry, omega T by omega. Okay. Fine. So if I want to maximize this gain, obviously, what do I need to do? I have to ensure, see, Rs you cannot change, right? Rs is given by the source. Omega you cannot change. That is the frequency at which you are trying to design for. The only thing that you can change is this ratio of GM over CGS, right? So if you have to maximize your effective transconductance, you have to essentially then maximize the ratio of GM over CGS, right? So the maximum ratio that you can get for a particular technology is fixed because GM is linked to CGS or CGS is linked to GM, right? If you have designed something for the maximum value of GM for a particular W by L and you want to increase it further, then the only thing you can do is to what? So let's say I have set up my transistor for, I mean, this type of problems you are going to face during design. So let's say I want certain GM and I have certain CGS associated with it. Okay. So I want to maximize this GM over CGS. So what should I do? I have two handles. I have W by L and overdrive. So what should I do? Increase W over L. It will increase GM, right? For a fixed overdrive, right? We keep the overdrive fixed, and I increase W. That is equivalent to saying that I add another transistor or set of transistors in parallel, right? Right? Increasing W while keeping same overdrive means that I can take another transistor, put it in parallel, right? Doubles, right? So will it increase GM over CGS? Effective GM over CGS? No, it doubles the GM, it doubles the CGS. So the effective GM over CGS cannot increase. So simply increasing W over L is not going to give you increased GM over CGS, increased omega T. What else? What can you do then? Pardon? I cannot hear, I cannot see who is speaking. Okay, yeah, okay. You can vary V over drive. So you want to increase V over drive or decrease? Decrease. So if you decrease V over drive, your CGS, does it change to the first order? Doesn't change. Your GM, what happens? Increases or decreases? Okay, increase, decrease sounds similar. So goes up, goes down. Goes up. If you decrease V over drive, why should the GM go up? Pardon? For a fixed? But I have not told you, I said fixed overdrive. Fixed V overdrive, right? Sorry, fixed W by L. Fixed W by L. So you are assuming that, what type of biasing are you assuming? Are you assuming a constant current bias? Okay, let's assume constant current bias, which means there is a current source associated. You are not changing W by L, right? Because that doesn't lead to anything that we understood, right? So only thing is overdrive. You want to decrease overdrive. So current is same. You are decreasing overdrive. I presume that you are using that formula ID over V overdrive. But what is assumed in that formula? Something else is assumed. No. It's a square law, sure. But if you keep current constant and you keep W by L constant, then you decrease the V overdrive, then is current constant. Right? So there are three things, right? W by L, current, and overdrive. So if you have to keep current constant, the other two should change simultaneously. You cannot change one. Correct? So now, can you tell me if I keep W by L same and I reduce V overdrive, will GM increase or decrease? Go up, go down? It will go down, right? So essentially, if I have to increase GM, then I have to go up on V overdrive. Correct? Fine. So now how much can I go up will be limited by how much headroom I have, right? Because moment I increase overdrive, I may face problem with the saturation condition, and that's a problem. So for a particular technology, for a particular design, that is the maximum you can set it to. Beyond that, you cannot go, which essentially means that you are limited by omega T of your transistor. For a particular technology, there is a maximum omega T you can hit. You cannot go beyond that. Right? Which essentially means that there is a maximum upper limit to GM effective. Correct? And when you design, you have to try to ensure that you are close to the upper limit. Whatever that upper limit might be, you can figure out from simulation with appropriate headroom and all. You cannot do better than that. But you can do worse, definitely. Because all you have to do is increase CGS. I mean, if you want to do worse, you put additional capacitor in parallel to CGS. Nobody is stopping you from doing that. I can simply say, I'll put additional cap here, and your omega T will come down, right? Because this cap will add to CGS, so you can obviously do worse. But you would not like to do worse because of this reason, right? So given that, now the reason I spent some time on this is that even though in this top circuit, it looks like that capacitance is a variable that you have. I can increase or decrease the CGS. It's not. It's not a variable. You are limited by omega T. So you are not allowed to change. I'm not saying allowed to, but in a good design, it is unlikely that you are going to fiddle around with CGS or put additional capacitance in parallel to CGS. You cannot reduce, because parasitics you cannot reduce to the first order. So but you cannot put extra CGS. So now, given that the scenario, yes. Yes, obviously, you would like to keep minimum length. I cannot hear you. Yes, it is pre-assumed because I want to maximize W by L. I mean, if I am maximizing W by L, why should I keep L anything other than minimum? Yeah, well, that's good point. Really, I should have made. Fine. So essentially, you have to do everything that you can to ensure you are biasing your transistor for maximum omega t. Right? Okay. So now that is done. So now if I have biased my transistor for a maximum omega t, and for matching, I require omega t Ls to be equal to Rs, then the value of Ls is fixed. Right? This constant gives me Ls. Correct? So essentially then, assuming omega t is fixed, or we have selected omega t, your Ls becomes, since Lx is omega t times, sorry, Rs is omega t times Ls, your Ls becomes Rs over omega t. Okay. So that kind of pre-selects Ls. Now, the problem here is, at what frequency is this going to match? Note that the frequency at this guy is going to match is at 1 over under root Ls times CGS. Right? Because ultimately you are trying to cancel out these two. Right? So essentially, the resonance will happen at 1 over Ls times CGS. Correct? And there is no guarantee. I mean, in fact, this is not in your handle, in your control anymore, because of what? Your Ls is Rs by omega t times CGS, right? So what is this telling you? This is essentially telling you that your Ls is being fixed. Ls is not in your control, and you have designed CGS for some value, and now you want to ensure that this omega naught also hits the condition that you want, right? So naturally, you see, you are in constraint of variables. Now you might say that, okay, in this case, it looks like Rs and omega t I cannot change, but what about CGS? I can change CGS as long as I change GM also, right? GM by CGS is constant, so I can change GM also. But in that case, you might end up with a situation where you require very large current, right? Because you need to then ensure that, let's say your CGS requirement is higher, then you also have to increase GM. You cannot independently change CGS without changing GM, which means you need multiple of these in parallel. So which means you end up burning a lot of current, right? So that is something that we definitely don't want. So essentially, the problem is now, even though it looks like this is going to work, we have a limitation with regards to placing the center frequency at the point that we want, placing the resonant frequency at the point that we want, while ensuring matching and good gain and all those things. So whenever you have these type of problems in circuit, you essentially are telling yourself that I need another variable, another handle. Right? In RF, the good thing is that if you have the thing that you are trying to optimize or fix is a resonant frequency, you can always place an additional inductor or a capacitor somewhere and then move it around while ensuring other things are not getting affected. Right? So here, all we can do then is place a maybe an inductor here. Right? I do not want to place an inductor in series with ILS because that's going to move many of the other things, right? Your match is dependent on LS, right? So your resonant frequency is dependent on LS. So whenever you have some variables which controls, whenever you have some component which controls multiple variables, it's better not to touch it once you have fixed it, right? Try to introduce something else which can control only one variable. Try to introduce one component which can control only one variable. If I introduce an inductor, then it will not affect your real part. It is only going to affect the imaginary part, right? Which essentially means that I can then move the center frequency or the resonant frequency around. Does that make sense? Okay, fine. So what I'll do is then Then additional inductor, call it LG. Right. So now your effective impedance here, Zin, is j omega LG plus LS plus 1 by j omega CGS plus the real part. The real part doesn't really change because the real part was looking in from here. The real part was omega t times LS, right? And this LG is basically coming in series with real part, right? So that doesn't change. So essentially you end up with omega t times LS. Okay. So now your omega naught can be under root CGS times LG plus LS, right? So now when you have fixed your GM, you have fixed your omega t, you have fixed your CGS, you fixed your LS, you only want to move around the resonant frequency. You can basically play around with LG. So to move so use to move omega. Okay, fine. Any questions so far? Okay. So that is as far as the your short circuit current is concerned. I mean, setting the resonant frequency while keeping the short circuit current to its maximum possible value is concerned. But the reason we want to do LNA is because we want to understand what is the noise figure associated with this guy, right? So that is something then that should be the next line of analysis, right? So the reason we are doing this is because the assumption was this configuration is going to give you better noise figure than putting a explicit resistor or a common gate configuration, right? So that's the next thing that we should analyze. Okay, so let's do that. Yes. 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 Right. So if we had put here additional, then obviously this guy would have changed, right? So that we don't want to do. So that's why we are basically, I mean, this is not an RF principle. This is any design principle. Moment you have one component which varies multiple things, then try to fix that component with whatever way you can, and don't change that, right? Then try to introduce another variable which changes. I mean, I'm pretty sure in two-stage op-amps, when you do, you also see the same thing, right? If you start off with DC gain, you have a problem. You start off with UGB, then kind of fix the GM, then you do whatever you want to tune the DC gain, right? So, okay. So let's analyze the noise figure. So to analyze noise figure, I'll assume the LG is not there because the LG is just moving around the center frequency. I'll analyze the noise figure with whatever center frequency I get, and then I assume that you will get the same thing up with LG, right? So that's the assumption. This is not required, so it gets shorted. So the noise due to RS, I don't need for analysis of noise figure because I know that will be 1 plus, right? So in the noise figure analysis, the contribution of RS becomes 1 plus, then whatever in the numerator by something in the denominator, right? So I will not explicitly find out the noise due to RS. I'll just find out the noise due to the device. Okay, and then we'll do noise figure analysis, putting everything together. Fine. So ultimately, what are interested in? We are interested in this I out, right? Okay. So now, what is this I out doing? This I out comes here, goes through this inductor LS, and part of it goes through here, right? When it comes to this node, it splits into two. One part goes through LS, other part goes through this loop, right? So you have to take this into account and note that these two currents are correlated. I cannot independently do the analysis and then add up in power. This same current is flowing through two different paths, which means I have to do a combined analysis, right? Okay. So if this is how I am going about analyzing this, then what is the current? What is the current through the GM? If I look at it at this node, if I look at it at this node, so the I naught is flowing out and IN is flowing up towards that side, right? So what is the effective current that is flowing down? So this is also I naught, right? Because if I naught comes out of that terminal, this is also I naught. So what is this current? I naught minus IN, right? So, okay. Sorry, minus of this, IN minus I naught, right? Yeah. Right? Okay, so let's do the KCL at this node. So what do you get? IN, so this ID plus I naught plus IN is equal to 0. Is that whatever? So if this is ID. Okay, I have assumed this IN to be this. Okay, fine. So essentially ID is negative of I naught plus IN, right? So negative of I naught plus IN. Fine. Okay, so if the current through that GM is this much, I know the VGS basically divided by that current, right? So your VGS is negative of IN plus I naught by GM, right? If I know the VGS, I know the current through CGS, right? So your ICGS is essentially, so if I have to give a direction now, so this is the ICGS, essentially negative of IN plus I naught over GM times J omega CGS, right? Okay. So then what is this current? This is I naught. So I'm to find out this current. This current is basically ILS, is essentially I naught minus ICGS, right? So I naught plus IN plus I naught over GM J omega CGS. So what I'll do now, I have both the currents. What I'll do a KVL in this loop. Then I'll get, I'll have another equation to get the relationship between I naught and IN. Okay. So KVL at this loop essentially means that negative of ICGS times RS plus 1 by J omega CGS plus a negative of ILS, right? If I am going around the loop, so it will be negative of ILS times J omega LS should be equal to 0, which essentially means that I'll just plug in these values. So negative of ICGS is N plus I naught over GM times J omega CGS. Yes, then negative of ILS is minus I naught Uh, Something is wrong. What is wrong? Yes. Okay, so I'll come to that. It is more messy to do input referred source in this case. I'll come to that. Why? Once we do the analysis. Something is wrong in the analysis. I messed up the sign somewhere. Huh? Right. This should be plus. Right? So no, hold on. So your ILS is here I made the mistake, right? So in this I made the mistake. So your I naught is going in, ICGS is coming out, so ILS is I naught minus. No, if that is mistaken, then everything else is mistaken, right? So no, you mean this is correct? This is not correct, right? Yeah. So this is incorrect. So next one we'll see, right? So here I have another problem. So this is correct, right? So I am going by, so drop across this, plus drop across this, plus drop across this in this direction, right? So basically, I mean, current down through LS is negative ILS times G omega LS. So that is also fine. So all I have to do is plug in these values. So this becomes plus here. This becomes plus. Correct? So this is equal to 0. So now times J omega LS, right? So I'm doing times J omega LS is equal to 0. Okay. So this might look a bit messy, but you have to understand that we can easily invoke the condition of resonance, which means many of these terms can get cancelled out, right? So what I'll do is, I understand that this guy and this guy can cancel out in resonance, so I'll club appropriately so that I don't have to do a lot of algebra. So what I'll do In plus I naught by GM times J omega CGS, I'll take as is. Then from here, I will take this 1 by J omega CGS. And from here, I will take this J omega LS. Right? Huh? Yes, correct. Yeah, basically here, this will be J omega L, right? So then it's fine. So I made double mistakes. I made many mistakes. Fine. Okay, fine. Which equation are you talking about now? Huh? Right. I out minus ICGS, correct. Oh, I plugged in the wrong value there. Okay, understood. Okay, this is plus. Agreed. Fine. So where is the error then? Because I have the ILS is that is double plus, right? Yeah, correct. Yes. Thank you. So I am running ahead of myself. That's the issue. Correct. So then what happens? Then to rewrite this guy is very messy otherwise. Okay. So minus ICGS times RS plus 1 by J omega CGS plus things wrong. I messed up somewhere badly. Where did I mess up? So let's look from the beginning. If that current is I naught, this direction is IN, this is I naught, that is also fine. Fine, that is okay. So VGS is also fine. It's okay. This is I naught minus ICGS. This is also fine. So you get negative ICGS times this. Plus omega ILS. Is also fine. Okay. Okay, I think let's go ahead with it. Maybe there's nothing wrong. I'm just, let's trust the algebra. Plus ILS times ILS is I naught plus IN plus I naught by GM times J omega CGS times J omega LS is equal to 0. So I'll just plug in the value of ICGS, which is equal to this, which is negative of IN plus I0. So negative become positive. So IN plus I naught by GM times J omega CGS times RS plus 1 by J omega CGS plus I naught J omega LS plus IN plus I naught over GM J omega CGS times J omega LS is equal to 0. Right? I hope you are following the algebra, right? Okay. Because I am not trusting my algebra now. So I'll club these terms, right? So I'll just take IN plus I naught over GM times J omega CGS. And I will club this term and this term together. So the reason I'm clubbing that is because you see that whenever I can get J omega LS plus 1 over J omega CGS, I can say that they're resonance and they will go off, right? And simplify the math. So I'll just say J omega CGS plus J omega LS. This is one, and I'll club the rest of them together. plus I get j omega CGS. So this entire term I naught IN plus I naught over GM times j omega CGS times RS. This is one term plus I naught j omega LS is equal to 0. Correct? So at resonance, this term goes to 0, right? Only left with this term. So I'll just play around with this term, which essentially means that your IN plus I naught over GM. This j omega also goes off. So you get CGS times RS plus I naught LS is equal to 0, which means IN by GM times CGS RS is equal to negative of I naught LS plus CGS RS over GM, which means fine. So your IN becomes negative of I naught. I multiply with GM CGS over RS, so you get GM CGS over RS times LS plus 1. Correct? Fine. So now note that this term is something special because this is omega, by CGS, right? So GM over CGS is omega T. Omega T times LS is RS because of matching condition. So this is 1, right? So it essentially becomes minus I naught times 2. So your I naught becomes minus IN by 2. Right? After all this algebra, pretty simple output, right? But the key thing to note is that your output noise, only half of the output noise, half of the transistor noise comes to the output. Okay. So which essentially means that therefore your power spectral density of the output due to this SI naught is AT gamma GM. Correct? Okay. So now what is the noise figure? So noise or noise factor is 1 plus. 1 plus is because of the contribution of the RS, which anyway will be there. The signal and the signal will be applied here, and the noise also comes in series. So the effect of signal and RS are identical. So that gives you that 1 plus. 1 plus, then the noise due to the device alone. So that is AT gamma GM divided by the noise due to RS alone. Well, noise due to RS alone is 4 kT RS times the transconductance, effective transconductance that we got. What is the transconductance that we got effective? This guy, right? So 1 over 2 RS omega T over omega. So 1 over 2 RS omega T over omega whole square, right? So what do I get here? So KT goes off. Gamma GM. So this 4 also this goes off by RS times RS squared omega by omega T whole square, right? So this one cancels, so it becomes 1 plus gamma omega by omega T whole squared times GMRS. Okay, so this becomes your noise factor. Now note that what are the design variables that you have? Firstly, if omega is much less than omega T, then this AF is almost close to 1. Right? Which means noise figure is almost close to 0 dB. This is much, much better than what you could have gotten with this common gate configuration, the one that you are doing in your assignment, or even putting a register, an explicit register. Okay. Now coming back to Abhay's point, that why are we not doing this input referred thing? The reason we are not doing this input I mean, you can as well do input referred, right? But the reason we are not doing is you have to deal with correlations, right? So the input referred stuff is useful when you want to give it as a model to somebody who is driving your blog, right? For when you are doing your own analysis, then you have to make a call which analysis is simpler. If the input referred is simpler, if the input referred doesn't have any correlation, then surely. But in this case, input referred will have a correlation. So that is why we generally tend to not do input referred if possible. Right? So this is a judgment call based on which algebra is simpler. But if you have to give it to somebody, give your LNA to somebody, then you have to give the input referred model. That is nothing you can do. Right? So now, as a designer, this is a good thing here because it looks like I can get substantially lower noise figure than with respect to the other configurations. But the thing here that you should be mindful of is to see that this noise figure looks like the excess noise is directly proportional to RS, right? And looks like RS is not in your control, which means if omega gets closer and closer to omega t, right? So even if omega is like 1/10 of omega t, then also this probably is okay. But if omega gets like, let's say your omega t is 100 gig and you are trying to make a 30 gigahertz circuit, then omega by omega t is 0.3, squared is like 0.1 approximately. So it probably might not be too wise to do this type of this configuration blindly. Okay. So one of the things that people tend to do, that's why, is to say that, can I reduce RS? Now you might say that, how can I reduce RS? Because RS is given by the whatever requirement, right? But the key thing to note here is that, can I put something between the RS, effective RS, and my block, so that the effective impedance looking in is less than RS, right? So what I'm pointing to is, this is RS, and this is your LNA. So if I put something here so that this is less than RS, then I can reduce the effective noise figure. Make sense? Right? So what is the simplest thing that I can put? I can put a transformer. And I want to reduce it by whatever, turns ratio squared, right? So this has to be n:1. So this becomes RS over n squared. Then your noise factor naturally goes down, right? But the thing that you have to note here is that you cannot simply do this and assume the noise factor goes down, because if you simply do this, what will happen to the matching? Because you have designed this input impedance to match to RS. You have not designed this input impedance to match to RS over n squared. Yeah, right. So here you have to ensure that this matching is RS over n squared, which means you have to ensure that omega t times LS is equal to RS over n squared, not RS, right? So you can still do this because this is GM over CGS. LS is equal to RS over n squared. So, I mean, you ensure that your LS is whatever. LS is originally RS over n squared omega t, right? So this is doable. This can be done, not an issue. But it is a handle that you should be aware of. Now, the thing that can go wrong if you do this is, we have assumed, I mean, obviously, instead of using a transformer, you can use all sorts of matching networks that we have discussed. But the thing that we have neglected here is the resistances associated with the matching network, right? So there will be resistance associated with the matching network, right? Even if you use these very good transformers, they will have a resistance, and they need not necessarily be much lower than 50 ohms, right? They can be as high as 10 ohms also if you want to if this n:1 is on chip. and you are trying to get very large turns ratio also at reasonably high frequencies, right? So you cannot neglect that. So what happens if I basically then what I'm saying is you have RS, maybe you have another resistance. I call this RG because it's basically getting connected to gate. I'm not showing the matching network now. I'm just assuming there is an RG associated. Okay. So what impact does this RG have? So in the noise factor, again, the good thing is that this RG comes in series with RS, right? So all it will do is that, the original terms will be there. So 1 plus whatever I have, what did I have? Gamma omega over omega t whole square GM times RS. Then additional term will be there. What will be that additional term? Can you quickly tell me? Basically, this RG will contribute to additional term in the noise factor. What will that be? If RG was equal to RS, what would that term be? Extra noise be? Yeah, you will have everything in the numerator and denominator also. If RG were equal to RS, the additional term would have been how much? RG by basically 1. So this, if RG is not equal to RS, basically RG over RS. Okay. Okay. So now the thing is, if RG becomes not very negligible with respect to RS for whatever reason, then you see that this, there seems to be an optima for RS, right? So because this term, the first term is essentially with respect to RS. This first term is, I simply am, okay, so let's say I plot this term. This is RG over RS. So this goes like this, and this term goes like this. Correct? So there seems to be some optima. And the optima in this case, whenever you have x plus 1 by x kind of thing, the optima is always when these two are equal. So, you differentiate and set to 0, whatever you want. So when these two terms are essentially equal, what is your optima? RG over RS becomes gamma omega over omega t whole square GM RS, or your RS opt. Under root RG by gamma omega by omega t whole square times G. Right? So what I basically am saying is that you cannot really go crazy with putting these transformers. Moment you put transformers or any additional matching network, it will have loss, it will have R. And if you have that, and then if that R starts to dominate, then you have to see what is the optima, what is the possible optima between this and that. And then there is a solution. There is a deeper need for this. We still have time, right? Yeah. So there is a deeper need for this because I have neglected a noise source which appears at higher frequencies, which I'm going to introduce now. So the reason I have neglected till now is to basically to make the algebra simpler. But now if I introduce a noise source, you will see that why this effect of RG sometimes might not be, cannot be neglected, especially when you are designing anything for higher frequencies. And that noise source that I'm talking about is this. So when you have this MOSFET, so you have this channel in the MOSFET, and the current that the noise current associated with the MOSFET is basically, let's assume these are incrementally shorted. So the noise current associated with the MOSFET, we model it as I drain, right? I drain noise. and we assume the current comes out as is, right? But you should understand that this is a capacitor, right? Which means that if there is the root, and this channel has a resistance, it's a distributed resistance, and you have a capacitance throughout, which means if there is fluctuations in these resistances or noise or voltage getting developed in the channel due to these fluctuations, then there will be some effect through this capacitor. So part of the current comes out through the capacitor as well. And this current obviously is correlated with IDN because the root cause is the same, right? So you have IGN current also comes in, and this is not an input referred current, by the way. This is an actual noise current. Okay. So naturally, IGN is correlated with IDN. If you take the correlation into account, the algebra becomes extremely messy. There is a 1970s paper on this by Van der Zeel. He takes into account all sorts of correlation and comes up with an expression. And then there is another paper which shows that even if you neglect that correlation, it's okay, right? So you just take that expression, assume it is uncorrelated, and go ahead, right? So the thing that you should that we understand by now is that this IGN at least should not appear at low frequencies because capacitor is open, right? So that's why when you do analog design, like 10 megahertz, 100 megahertz bandwidth, even a gigahertz bandwidth, say fine, not required. IGN is anyway not there. But when you are doing multi-gig, right, 10 gig, 30 gig, then you cannot really neglect that. They become substantial. So it is intuitive to understand that this IGN will have a high pass profile, right? Because coming through a capacitor. Right? As it turns out, your IGN expression is approximately equal to GM over 5 omega by omega t whole square. Sorry, this is the effective so if I say that IGN, its power spectral density is 4 kT 4 kT times some GM, right? Effective GM, I should say, we have a different terminology for this. 4 kT times time GIGN, then that GIGN is approximately equal to this. Now, the value of this expression of this is not important. The part that you should focus on is it has a high pass shape, which means it is as frequency increases, this becomes more dominant, and it is also proportional to GM, right? So that makes sense because the original IDN was also proportional to GM. This is also proportional to GM, right? So the reason this becomes important is, so when I said I have this RG, now this RG is not only the loss due to not only talks about the resistance associated with the matching network, it also can be thought of as equal to some whatever you had RG naught plus 1 over GGN, right? So GIGN rather, so this term. And even if you are able to reduce the physical resistance associated with your rest of the stuff, this is fundamental. This will be there because it comes with a MOSFET. And if you are trying to be too cute and say that I want to save power, which means I am reducing GM, then this guy is going to dominate. So in the course project that you are going to do, this will not be problem because the omega t will typically be much higher than omega. But if you are, let's say, go out in the industry or in your research project, you plan to design a 30 gig LNA or 60 gig LNA, then you cannot neglect this, right? So as far as few gigahertz LNAs are concerned, when you are using 65 nanometer, 45 nanometer, 28 nanometer, doesn't have a role to play. The physical resistance is more important in that case. But if you are going for higher and higher frequencies, then this starts to become dominant, right? Okay. Any questions so far? Okay. So the good thing about putting this, I mean, now let me come to some of the practical situations, the practical issues that happen in LNA design. The part that we have neglected till now is this. We have neglected CGD totally. But in real cases, you will have CGD. By the way, the other thing that I have neglected is at the output, we have only talked about short circuit currents. When the output, we are going to have a load, right? And typically for very good LNAs, you cannot have a very explicit resistive load. Generally, what is done, you put another resonant network, or you simply put an inductor, right? And the inductor gives you the load. But if you do not, if you are not getting sufficient impedance because of inductor only, you resonate it out. And there will be a, not RS, should be R in. And you are going to get this RD is going to give you some real part, and you essentially get a output because of that, right? So this also helps in reducing noise. If you put an explicit resistor, you will lose headroom, you will increase noise, all those things that are going to happen, right? So the issue now is this: if input swings, this guy is going to swing much more based on the gain that you require, which means you are going to have these CGD interactions. And this can be substantial if the gain is high. And the effect of this you can think of, I mean, I will not prove this. You can do the algebra to figure out. But intuitively, you can think of if this guy, the effect of this CGS and the effect of this CGD are coming in essentially parallel. Correct? So, which essentially means that the input impedance is, I mean, CGD coupled with LS was giving real part, right? That was a matching part. So if I have another CGD which gives another real part, and these two come in parallel, which means the effective impedance goes down, right? So you design for matching, that goes for a toss. So that's a problem. So another problem that if you recall, one of the when we were discussing about transceiver architectures, we talked about LNA is followed generally by a mixer. There will be switching in the mixer, and there can be coupling between mixer and the input of the LNA, which causes LO feed through and all those things. If you don't remember, go back to one of the initial lectures to figure out. So, and that feed through generally should happen through CGD. That is the only way this becomes a bilateral device, right? So a lot of issues with CGD. So the general thing, what is the easiest way to get rid of this issue? You cannot change the size of the transistor of this GM because that has so many other implications. Given that you have fixed the size and CGD will be there, I do not want to have this issue associated with CGD. What can I do? Cascode, right? So cascode I can put, so I'll put a cascode. Fine, so this cascode will be biased. Let's say I bias it with VDD or whatever. And there will be a capacitance associated with this node, there will be capacitance this node and so on. So this will essentially, I mean, this will not completely mitigate the effect, but it will definitely reduce it because, or not eliminate the effect, it will mitigate it because now the swing at this node is not as much, right? If I assume that I have a RL, whatever be the value of the RL. So the most of the swing happens here. And here you have lesser swing, right? So effect, even though CGD still exists, its effect is not as much, right? And also that is the feed through between whatever is connected to the mixer side to this node is even lower, right? But the issue is the point that you should be concerned about. What about, I mean, we did put in so much effort to reduce the noise. Now you're putting a cascode device, which is again noisy. So won't it cause a noise problem? right? So this guy will also have this noise. Now, what do you think? Will this cause a noise problem or not? So now consider this cascode in isolation in the sense that, and let's say I neglect the channel length modulation of the bottom transistor, which you cannot neglect in principle, but let's say we neglect. So this is the parasitic capacitance and CGS, CGS. So can you comment at low frequencies what's going to happen? What will be the noise output due to this IN? Zero, right? All capacitors are open, the IN will circulate, right? So at least we know that at very low frequencies, this capacitor, this is going to be fine. But at high frequencies, obviously CP and CN are going to get activated and you are going to get a noise. And if you do the calculations, you are going to see that your effective I out N will be proportional to omega by omega t times I, right? So do it yourself to convince yourself that this is what it is. Where this omega t, or I should not say omega t, I should say omega t prime, because this is essentially GM of the cascode divided by CP plus CGS. So if you do the math, you are going to get this. Okay, so it will be GM of cascode by CP plus CGS. The reason this is important is that you cannot do anything with this GM by CGS factor. That comes with the technology, right? But you can do something about the CP. If this transistor is very, I mean, if you become greedy and really size this up, then the capacitance associated with this, because you have a drain to body capacitance, right, of this transistor. You have a drain to body capacitance of this transistor, and then you have a source to body capacitance of this transistor. So if the drain to body and the source to body capacitance start to dominate, then you are going to have this omega t prime is going to come down, which means your cascode current will start to dominate. Not dominate, at least start becoming prominent, right? So cascode, while it helps, is one of the very few things which almost gives you a free lunch, right? But you cannot go too greedy with sizing the cascode up. Okay, that is something that you should keep in mind. Okay. The last part of this LNA is, this is again not required for your project, but in a practical application, that the not a problem, the feature is when you have this, this is the pack, this is the chip, let's say this is a chip, and you have a chip boundary. And when you have a chip boundary, you have to just like when the chip has to interface with the external world, you have to put in some wires and connect it to the chip. So those things are called bond wires. You bond it with the external world. And as it turns out, the length of these bond wires are more than the dimensions of the chip, more often than not. So if I, to the scale I cannot draw, but if you get the idea, so this will be something like, the bond wire will be something like this. Here, something like this. And here you probably have a source. And here you have a ground, right? So when you have these long routings, they give inductances. Now, naturally, this inductance is not so bad in this case because you anyways want the inductance to be associated with LS and LG. But you should not size your transistors, or should not design in such a way that this LS becomes less than the bond wire inductance. Then you have a problem, because you will not, when you moment you put the bond wire, it's not going to work. So you have to keep some LS has to be higher than the bond wire with some margin. If the bond wire inductance is let's say 2 nanohenry, then that's an additional constraint on your design. You have to ensure that do not size your transistors so that your LS becomes less than 2 nanometers. Similarly, you have here, and if you say that, I mean, some packages give you very small bond wares, right? You can get like half a millimeter of bond wear, like half a nanohenry of inductance. Then you say that I can go greedy, but the thing with those cases is that here I have neglected the on resist or the resistance associated with this inductance, right? So if you say that I can, for some reason, I would like to increase the inductance, right? Because maybe omega t times Ls, I do not want very large omega t, because omega t very large means I probably have to want more power. So I reduce omega t and keep Ls high, but it doesn't come for free. It comes with the resistance of the Ls, which means there will be a voltage drop, DC voltage drop across the inductor, which means the effective GM is also going to go down. And not only that, you are going to get additional noise because of the Ls. So moment you have on-chip inductances, you have to take care of the noise. If you have on-chip, off-chip inductances, their quality factors are very good compared to the on-chip inductances by a factor of 3, 4 at least. So in that case, you have to take the existence of them into account. Okay, fine. So we'll stop here. Yeah, so hopefully this will be sufficient for you to go ahead with the LNA design project, which I'm going to post. Any questions?